It should be 9 p.m. on Qena, Egypt. Okay.
Yes.
Okay. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon and good morning, everyone. Today we have webinar, and for this month we present Dr. Ibrahim Abdallah Ismail Hassan. Actually, he is my friend when I was in Bath, University of Bath, at 2009. It was only 3 months. I was there in only 3 months, and in maybe 2 weeks ago, I chat him, and I asked him to give a lecture in our webinar, a monthly webinar. Inshallah, Dr. Ibrahim will deliver a topic regarding the photoelectrochemical processes, which is the conversion from solar to hydrogen. Yeah, I would like to read his CV, a short CV from him. So his name is Dr. Dr. Ibrahim Abdallah Ismail Hassan. He's lecturer in chemistry in South Valley University, Qena, Egypt. We call it Mesir, like in Indonesia, we call Egypt is Mesir. Before he got his PhD in photochemistry from University of Bath, UK. He studied chemistry from 2006 until 2011. And I was there in 2009. He was supervised by the supervisor is Professor Lori Peter and Professor Prang Marken. Yeah, and his PhD thesis or PhD dissertation entitled "The Solar Energy Conversion by Photoelectrochemical Processes." And today he will deliver a lecture regarding the solar to hydrogen conversion via nanostructured solar cell. Before, he also as a visiting scholar at York University. York University is not in UK but in Canada, the Faculty of Environmental Study in Ontario, Canada. Now he is a lecturer in Department of Chemistry, South Valley University, Qena, Egypt. So, Dr. Ibrahim, I also call him brother. It's my brother. Brother, you have 40 minutes, 40 or 45 minutes to give a lecture, and we have maybe 15 until 20 minutes to question and answer. So the times is yours now. Okay.
Thank you, Adi, and I'm trying to sort out how can I share my screen.
Okay.
It should be
in the middle, the green button in the middle.
Yes, I do, but it keeps asking me to go to setting and let or allow Zoom to share my screen.
You already.
So, did you see any screen or any?
Okay, yeah. Try. Just try once again. Is it? If you need, maybe you can send your file to me, and so I can share for you. If you have difficult to.
Yeah, I will do. I will do. Maybe it's easier. Larger than 100 media, so I can remove some. the video. Let's see.
Okay. Okay. What is it? Dia kan host. You can start sharing.
Did you receive it, Brother Adi?
Sudah jadi host. Dia co-host kok. Ini kalau ini cuma all participant. Okay. Can you?
I sent to you by through the WhatsApp. Did you see?
Okay,
did you receive it?
Not yet. Not yet. Maybe in 1 minute. Just 1 minute. Just wait.
Oh, yes.
Okay. Maybe you can start. Yes. You can start, and I will wait. I'm waiting for the file.
Yeah, it can't be sent by WhatsApp. So
okay. Okay. I write my email to you.
Yes.
Okay.
Did you receive it?
Maybe yet, not yet. Just wait 1 minute, maybe 1 minute, in 1 minute. Usually, because we are using Google platform, and maybe you are. In a minute. Okay. Not yet.
I will send it again.
Okay.
Yeah. Yeah. A few seconds. It's downloaded.
Is the files big, or?
It's I mean it's 15 megabytes, so it could be sent.
Okay. Bisa share screen ya? Kamu juga nggak bisa? Bisa. Nggak tahu. Maksudnya nggak ada tulisan apa only broadcast gitu. Have you upload the email?
Not yet. Security.
Okay, just wait a minute. Okay. Not yet. Maybe you can try to share your screen once again. All the audience, maybe wait a few seconds. We try to Dr. Ibrahim try to send the file to us. Wait a minute, I don't know what is the problem, because he already sent the file using email, and also I don't know, it's not working, and I don't know what is the problem. Maybe I send you another email for you. Maybe it's working for another email.
It's downloaded, brother Adi. So it's still.
You mean you upload it? You mean still
upload it? Yes, upload it. Yeah, I mean. So I sent it to you now.
Maybe you can try to open and just give introduction before, or just while we are waiting for the email.
Okay.
Okay.
Did you receive?
It's already, yeah, I received.
Okay.
I received the, okay. Yeah, you can start. Just start. I will share for you. Okay. Can you see the?
Yes, I do. Yes. Thank you very much for your nice introduction and for having me. And I am extremely sorry for this interruption and not be able to share the screen. So my talk is basically about solar to hydrogen conversion via nanostructured solar cell. Can you hear me clearly?
Yes, very clear.
Great. So what we are aiming to, so I think you are the one who control the screen. So can you?
Okay. Next. Just
next.
say next. Yeah.
Yeah. So what we aim is producing hydrogen from solar energy and water, and then use it in fuel cells to produce electricity, and the only side product is water. So next. So why do we need renewable energy? There is no doubt the importance of energy in our life is very vital for our life. So the main source of energy we have right now is fossil fuels, which is finite and polluted. Next. So the pollution comes by climate change. What is the climate change? Is the fumes and toxic gases which come by combustion of fossil fuels, which leads to global warming and next. Desertation and forest fires on forest. Next. And melting the ice, which lead to in the end of flooding. Next. And maybe sinking of many cities. Not just even sinking of many cities, but also it have high impact impact on health of human. Next. This impact of on the human health, like it can cause many different diseases like asthma or cardiovascular diseases or malaria or diarrhea, or all this kind of diseases can be caused by climate change. We can divide it like 4 areas, like rising temperature, which lead to severe weather, which can cause injuries and mental health impact even. And also it can lead to extreme heat, which we suffer in summer from, which lead also to illness related to health, to heat, and even cardiovascular failure as well. Also, it can cause more extreme weather, which like air pollution, change in vector ecology, which also can cause lots of diseases. Melting of ice can rise the sea levels, which means the drinking water can be polluted and can lead to more diseases as well. Next.
Sorry.
So to solve the problem of climate change and to find another source of energy instead of the finite energy of fossil fuels, we can imitate the nature. The nature happens something called photosynthesis, in which the plant absorbs sunlight and capture carbon dioxide to produce oxygen and carbohydrates or sugar or food or energy. So we can try to make like imitation of this, which is called artificial photosynthesis. Next. So artificial photosynthesis we can like make solar cells which can capture or absorb the solar energy, and then water splitting occurs, producing the hydrogen. Hydrogen can capture even carbon dioxide, so we can use hydrogen as a source of energy, or we can like insert carbon dioxide, which even minimize the emission of carbon dioxide, and produce methane, which also a source of energy as well. Next. So what our aim of the study or our research is to use the huge amount of sun and the huge amount of water, little of them, to produce hydrogen, which can be used in the fuel cells. And you can see in London, for example, since decades, even some buses used to run by fuel or hydrogen fuel. And nowadays, it's spread everywhere in the world, or many ways in the world. So we can see sun sends in 1 hour an energy which enough for the whole world, for a period. So in the same time, water like covers about 71% of the whole Earth surface area. So we can use a little of them to produce or to store this kind of energy in chemicals, which is hydrogen. Next. So in the fuel cells, what happens is hydrogen, H2 gas, can go through a membrane, deionize it. Deionize it means it gives H protons and electron. For that, even it's called energy carrier. Yeah, not just a source. It's just it's called energy carrier because it carries the electrons from the photons of the sun and then give them in the fuel cells to produce electricity, which is able to do the work, and then the H protons can combine with oxygen from the air to give the only side product, which is water. Next. So it's very easy to put like hydrogen tank in a car or any transportation mean, and then joined with like fuel cells. Fuel cells produce electricity, which can do the work and operate the engine. And the air coming from oxygen coming from the air. And the only side product is water and heat. Next. So hydrogen simply can be defined as the simplest and the smallest and the most even abundant element in the universe. It's like it's just one proton and one electron. It even doesn't have a neutron, which locates in the first place of the periodic table. Occurs generally as a gas, and it can be used as an energy source through combustion, or an energy carrier in the fuel cells. Next. Lots of sources can be used for production of hydrogen. Unfortunately, nowadays, most of these sources coming from fossil fuels, like coal, oil, through gasification or fermentation by biomass, and even from natural gas can be steam reforming with carbon dioxide. But we're trying to focus in this area, which is solar energy through electrolysis of water, photic splitting of water, thermal splitting of water, and even the wind, hydro, any kind of renewable source of energy can be used to electrolyze water and produce hydrogen. and even the fission and fusion in the nuclear reactions can be used also to produce hydrogen, which is a very good store for energy in the sort of chemicals. Next. So let's speak about like little science. I know maybe most of the audience are not very specialized in this area, so I will not. I just speak in the basic way about hydrogen production through solar cells, or specifically nanostructured solar cells. Why nano? And even from no-cost materials. So to minimize the price of the unit of hydrogen. Nanostructured means with a little amount of chemicals, we can spread very large area of substrate, so we can produce a cheaper unit of energy. And water splitting, we can divide by next slide. Is like into oxygen and hydrogen, which can be done all either thermally by heating water like 2,500 degrees Celsius, or photoelectrochemically by using photoelectrochemical cell, by using sunlight and electrolysis cell, or even by normal electrolysis by using any source of electricity, either sustainable source or from fossil fuels. In the photo system, in the photoelectrochemical system, both excited electrons in the conduction band and the holes in the valence band are participating in the in water splitting process. So if we have a look in this figure, we imagine this like the electrode or the semiconductor material which used to produce the working electrode in the solar cell. So when it hit by photons of the light, it absorbs the energy, and excitation of electrons occurs, which migrate into the or moved to the conduction band. So from the valence band to conduction band, the electron moves, and then the holes migrate to the interface between the electrode and the electrolyte, which is aqueous electrolyte, and oxidation of water occurs. But the electrons migrate to the counter electrode, which is a catalyst, and the whole amount of electrons accumulated to produce hydrogen. In fact, this amount of electrons is not enough to produce hydrogen. So sometimes it needs another source of electrons, which can be sourced from another solar cell, like dye-sensitized solar cell, for example, titanium dioxide, which is made by micrograd cell through the tandem cell. But I mean, this is like basic idea of water splitting. There are some questions in the same slide, Brother Adi. You can click next, so to see the equations. So these the two main processes, like anodic oxidation, in which oxidation of water occurs through or via holes on the valence band or the interface between the electrode and the electrolyte, and oxygen produced. And in the cathodic reduction, where the H protons can be reduced by electrons in the conduction band and hydrogen gas produced. We can even see the bubbles of hydrogen on the counter electrode in some experiments. Next. Next. So just a brief next. How we can prepare like nanostructured electrode which can be used as a working electrode in the solar cell. I stuck for like very low equipment, basic equipment, and because I know I might not be able to offer like very expensive laboratory, so we use like sol gel doctor bladed method to prepare nanostructured solar cells via making a paste from, for example, tungstic acid, H2WO4, which by ignition through like 500 degrees and can convert to tungsten oxide, which is the semiconductor which works as a working electrode in the solar cell. And this conducting glass, which is FTO or fluorine doped tin oxide. And in the normal case, there is no any connection. And by the hitting the light of this material, which is semiconductor material, the electrons absorb the photons, which make it like excited and move from the valence band to the conduction band, which make the material to be conductor. And we can use the electrons for our work. Next. Next. So we use another method which is called layer by layer method, which is very simple as well, can be done in any laboratory with any with very basic tools. We can use this electrostatic force to prepare nanostructured iron oxide solar cell or solar electrode via deposition or layers of iron oxide through dipping the conducting glass into iron colloidal solution, and then in an organic binder like phytic acid, which is binder, for example, this the ITO or indium doped tin oxide, which is a conducting glass, and then when it dipped in colloidal solution of iron, it gives the first layer, and then another layer by phytic acid to make binder between the two layers of iron oxide, and so on. Many we can make like many layers, and in the end we can ignite. Next, brother. We can anneal or anneal at 500 degrees for 2 hours. So the phytic acid, which is organic compound, can be decomposed and leave only the iron oxide stick on the conducting glass. Next. Another method as well, very simple method, which is called spray pyrolysis method, and it's a very simple kit, which is like a spray bottle pyrolysis kit. Where, for example, if we want to prepare iron oxide electrode, we use precursor solution of iron salt, any salt like iron nitrate, trivalent, and like mix it with dissolve it in 1:1 methanol and water, and then put it in this small bottle, and then by pushing the rubber we can spray very little droplets, which make nanostructured iron oxide, especially by annealing and producing crystals of iron oxide nanostructure. And in this book we can find like lots of information about these kind of methods of preparation of electrode. Next. And even we can use like very simple tools, like even like perfume spray bottle. We can use it for spray the substance which to produce nanostructured solar cell in a very basic way. At of course on a hot plate, like at 500 degrees, and then annealed, so we can produce the electrode in the nanostructured. Next. Then we can like make some characterizations like morphology, scanning electron microscope to see the nanoscale or the shape of the crystals of the nanostructured solar cell or electrode. And yeah, this like a sample, like very simple example of tungsten structured electrode is scanning electron microscope. Next. The other experiments we can do to investigate the photo activity of any materials, or either it's a new one, we just try to find new electrodes for solar cells, or to improve the efficiency of the known ones. We can do incident photon to current efficiency, which is called IPCE, to measure, for example, if we hit the electrode with like 100 photons and produce 50 electrons. In this case, we can say like the efficiency is like 50%. So the incident photon to current efficiency measured against the wavelength of the light. And it was found like 60% for the tungsten oxide, and it can be calculated through the next equation in the slide, Brother Adi. The IPCE for the cell can be calculated by the divided I current of the cell multiplied by IPCE of the photodiode, which is standard materials to measure the photocurrent response, and divided by the current, the photocurrent response by photodiode, which is a standard substance. So this is like a very simple way to explain the incident photon to current efficiency. Next. So yeah, another lots of examples like iron oxide prepared by spray pyrolysis, which shows like efficiency about 7% or 8%. This is called photocurrent response, which mainly is illuminated cyclic voltammogram. We put light on for like 2 seconds and light off for 1 second. And then we can see these peaks of course, from this this forward and this backward for like cyclic voltammogram. So when we see this kind of photocurrent response, we can say, yes, this material is photoactive material, means react positively with the light and can be used for solar energy conversion. And according to the amount of milliamp per square centimeter, we can say, yeah, this is enough for water splitting, or is not enough, or need to be provided by more electrons through another solar cell. Next. Yeah, another like family of materials to be used for water splitting or as an electrode of solar energy, solar cells, is like strontium titanate ferrate, which done actually accidentally by like measuring by mixing strontium, titanium, and iron salts, and then sprayed on hot substrate, and then by annealing it comes with this material, which was like maybe the first one I prepared this kind of, which called perovskite, like even before the discovering of perovskite, like 2008. And this like the scanning electron microscope, which sort of nano material, and the cross-sectional, which is like on the next slide, we can see it gives positive photoactive reaction. Next. So this is like XRD, which prove the chemical structure of the prepared material in the form of 112 orientation, with the similar to this chemical composition. Next. Yeah, the same material shows like considerably high photocurrent response with like 11% efficiency, which is promising at that time, and it could be improved actually, but I mean yeah, I mean we looked for other materials. So this kind of materials can be used for solar electrode or solar cells electrodes manufacturing or preparing. Next. Yeah, about the generation of perovskite, shows like very high photoactivity. For example, we tried with lanthanum iron oxide or lanthanum ferrate, which prepared by different kind of methods, which showed a considerable photocurrent response and in sort of nanostructured materials as well. And this material is good visible light photocatalyst due to its suitable band structure and environmental stability as well. Next. Yeah, this is a photocurrent response, which means, yeah, it's photoactive and can be used for solar electrode. Next. The same XRD shows the same structure, lanthanum iron trioxide, which is lanthanum iron oxide with these peaks, the red line and the red color, and the blue one is oxide of tin oxide, which is mainly found in the glass, so it's not important. So yeah, next. Yeah, this recent paper actually just put online like 3 weeks ago, and it will be published by Nature by Professor Domin in Tokyo University. And we can state it, which states that the most efficient solar hydrogen production schemes, which couple solar cells to electrolysis system, solar cells and electrolysis systems, which reach solar to hydrogen conversion about 30%, which means to produce enough hydrogen for our renewable energy source, we have to like build next, brother. We can build like a solar field, for example, solar cells field, and then produce electricity, and then convert the DC to AC, and then use this electricity to electrolyzed water, which can be produced hydrogen, which can be either compressed and put in the high pressure tank, or directly fill the transportation means and put in the station, for example. So this is, I think, the best way of achieving lots of goals to put hydrogen as a source or a carrier of energy in the soon future. Next. Yeah, it's a similar, similar slide going. I mean, to minimize even the cost of hydrogen, we can. It's like about $13 US a kilo nowadays, and it's planned to like minimize this price. So we can use nanostructured solar cells or low-cost material solar cells to produce electricity, which can analyze water and produce hydrogen. Maybe in the future, this can be done like high differential pressure electrolyzer. But nowadays we can it used like normal water electrolyzer, which might be slower in the production of hydrogen, and also can compressed and then put in the tanks or just directly in the hydrogen fuel stations to fill the cars. Next. So it's easy to build hydrogen stations, and then you can fill your car by hydrogen, which is it's very safe and very clean energy. Next. And even like from the smallest car in the world can work in hydrogen car, which is H Racer. Next. To the trains works with hydrogen. Next. Ships. Next. All these work by hydrogen until the rocks, which is used liquid hydrogen. We can support the rocks for a long time. So there are a lot of companies nowadays, of car companies, produce fuel cells vehicles. Fuel cells vehicles spread nowadays, especially like Tesla in US, which is electric car, and even any electric car can use fuel cells as a source of electricity instead of batteries. And even we can like compare between batteries and fuel cells. Batteries, if you left a battery like for a long time without using, you can lose the electricity stored in it. While like fuel cells or any like hydrogen tank, if you leave it like long time, you can lose any molecule of hydrogen gas. That means hydrogen is the best kind of store of energy or solar energy. Next. So by time the amount of vehicles sold increases like by these numbers in like in US $billion, like just 400 million increases to about 5 billion in 2020, and increases and it's planned to be like $250 billion by 2030, for example. So fuel cells vehicles increases in the market, and that leads to increase the hydrogen stations in the world as well. I mean, both of them, they will increase the existence of the other. So next. So hydrogen stations is maybe one of the problems right now. You cannot find hydrogen stations everywhere if you have a hydrogen car, but it can be solved, sort out this problem. For example, suggestion that every petrol station can have a small unit of hydrogen station to like provide for hydrogen cars owners to for hydrogen. But until now, not applicable this kind of solution. Next. So hydrogen station, we can find many ways in the world. We can see the places later. Next. And even you can have your own unit of hydrogen gas station in front of your house by a simple fuel can provide this unit which analyze water and produce hydrogen and store the hydrogen, and then you can fill your car by hydrogen in front of your door. So it's it could be applicable in one day. Next. Yeah, this is fuel cell stations, different wares. Next. Yeah, we can see like in 2021, January, these places in Europe, like the blue one is already exists. The orange one is planned to be built. Some in East Asia and some in America and Canada, US and Canada, and even one like two or in Emirates or something like this. So we need like to spread all these stations everywhere in the world so we can have no excuse to have a hydrogen gas car one day. Next. Yeah, this like by focusing in Europe, we can see it's still not too much, but it's we can see it's a lot of planned stations around Europe. So hopefully one day it can be spread. So we aiming to find like very healthy environment with solar cells, with like hydrogen stations, with clean energy source, and people can live in a very healthy life. So this is like a video you can watch. It's very informative and includes lots of facts related to this topic. And this like two like videos. I wanted to share some of it, but maybe there is no time. You watch it like in your spare time. So next. Expect this problem. So thank you very much.
Okay, thank you very much for Dr. Ibrahim for the very nice presentation. We are waiting for the question from the audience, but before I would like to ask about one question regarding the hydrogen energy. Which is better to get the hydrogen from what you already described explained before, that we convert from the water splitting, or from what we conventionally using pressure, like we decrease the temperature to maybe below 50, below minus 50, and we press the atmosphere, and we condense the hydrogen from the atmosphere, because which is more economic if we compare between water splitting and by or just distillation, gas distillation, according to your experience. So which is better to?
Yeah, if I understood your question, you ask about the in comparison of water splitting and water distillation, or converge in both
gas distillation.
Gasification.
Yeah.
Yeah, of course. I mean, by using fossil fuels, you mean?
No. Just usually we are using, like, for we get nitrogen, we get oxygen, and what we get hydrogen or oxygen usually using in the hospital. And usually here in Indonesia, we just give the high pressure to the atmosphere and decrease the temperature, and the gas become liquid. And
yes.
The gas become liquid, and after that we get this evaporation of the gas, and we maybe like we get 20% of oxygen, maybe 70% for nitrogen, and maybe 2% for hydrogen, because the content of hydrogen is around 2% in the atmosphere. So which is more efficient and maybe cheaper using water splitting, because actually for the water splitting is need a very high energy, because we have to split the hydrogen and oxygen, and compared to the conventional distillation, which is more efficient. This is my question.
Yeah, in like in the point of view of like economic, compressing the air is much maybe cheaper than to go through the complicated water splitting processes. But in the application point of view, to use, for example, pure hydrogen or pure oxygen is much efficient than to use them in a polluted, we can say polluted by the other components of air. Maybe even like, for example, if you use one cylinder of hydrogen, pure hydrogen, it's much efficient than to use like 20 or 100 cylinders of contaminated hydrogen by the other components of air. So maybe you can see even the economic is not that big difference. Yeah, I mean, so I mean, it's proper to go through the proper use of production of hydrogen and to be used effectively.
Okay, this is another question. How about the hydrogen station that is already built today in the world? What kind of the material? So what the kind of material that used to produce the hydrogen in the hydrogen station? Can you describe this question?
Yeah, as I mentioned, about 94%, around 94% of the whole produced energy in the world right now is unfortunately from the fossil fuels. So they try to produce hydrogen even from fossil fuels, which is polluted. But just to use hydrogen in like some use, for example, like inside the company, like indoors, or for some transportation used indoors. So we need very clean without any toxic gases indoor, you mean in closed place buildings, or in use them like in very specific way. But in the same time, they try to find like sustainable source of hydrogen by using, like, as I said, by building field of solar cells and use the produced electricity to produce hydrogen, and then can be used in providing the stations with hydrogen.
Okay, thank you. The next question is it safe enough to establish the hydrogen station in Indonesia, or maybe like probably in Egypt? If it is yes, what for us need to accomplish first to build the hydrogen station?
I can't explain. I'm not expert in this area exactly, but I mean, I think the people who are doing that, like production of hydrogen or establishing hydrogen stations around the world, they put like very specific rules to build stations. So if you want to build a station, hydrogen station in Indonesia, you can contact directly to them, and then they can provide you with the exact rules and very accurate advice.
Okay. Another question is from what kind of, because before you are discussing about the kind of material. So what kind of material, what the type of material, or what is the properties of material that is good to use as the catalyst for produce hydrogen? This is, I think this is your topic.
Exactly, yes. I mean, yeah, starting, I mean, because I stuck myself in low cost materials. There are very good materials in the third group of periodic table, like gallium, arsenic, and germanium. This kind of materials, which is very expensive and rare, is very, very good material for this purpose of production of hydrogen, and even for using of in the solar cells as well. But what the benefits of using gold, for example, or gallium or germanium or very expensive substance or materials to produce very expensive hydrogen unit or energy unit? So it will not be applicable. It will not be affordable for like many countries, many individuals. So I mean, not enough to find a very good efficient solar cells to produce hydrogen, but it's important to find a very applicable source of this kind of unit. It's cheaper, the cheapest source ever in the to produce hydrogen, which can easily used by all kind of people around all over the world. So I am stuck in this kind of low cost material like tungsten oxide, titanium dioxide, perovskite, this kind of materials. But I mean, for the fact of the science, this kind of materials, I said germanium, gallium, even silicon can be the best of production of hydrogen, but it's expensive.
Okay, have you compared the type of material, like what you already said before, that how to say, you said that germanium or so on and so on, silicon and so on. What is the best one? What is the best one? And why the best one is, what is the, how to say, what's the properties or what is the characteristic of the material that produce the hydrogen the best? Okay.
Yeah, I mean, yeah, I do understand. I mean, for example, some papers mention that gallium or this kind of expensive material can produce solar to hydrogen efficiency like 18%. But while the low cost materials can produce like less than 1% until now. So, but still, I mean, you can go and be happy to produce like a higher efficiency, but still the cost is very expensive. So, I mean, it's better to keep trying to use cheap or low cost materials to produce cheap or low cost energy unit, instead of leave all this behind you and go just be happy for the expensive ones, and then you can produce unwanted hydrogen, which is very expensive for the most of people.
Okay. Another case regarding the thermodynamics. Yeah, because water splitting and whatever is actually consume the energy. How about the efficiency of the production? Because you produce hydrogen and you need energy, and you use the hydrogen to produce the energy. So actually, we produce and we lost the energy. What is the efficiency? Yeah.
Yeah, I mean, you're right, but I mean, it's still not economic for like the research we do, and we're trying to find low-cost materials to produce hydrogen is not economically right now. But I mean, to produce hydrogen via solar panels, it's I think more useful, and it will be low cost as well, because what produce of electricity you can capture or convert to chemicals, which is hydrogen, and it can be lost until you use. Hydrogen can be lost until you use, but electrons in the batteries, or you can be lose easily, even if you don't lose immediately or sooner. So even consuming of energy to produce energy, but still the produced energy is much more than the consumed part of energy. For that, it's economically useful.
Okay, yeah. I think this one is the last question. It's from Dr. Gunawan. When you measure the photocurrent and ICPE, don't you think that it will bias the result if you use non-noble solutions such as hydrogen chloride, sodium hydroxide, usually for the measuring efficiency by using sodium sulfate? Can you answer about this question?
I mean, what I understood of this question is like, for example, to use this kind of solutions, which is called aqueous solution, because they work as electrolyte to carry that charge between the anode and the cathode, or the anode or working electrode and the counter electrode. Usually for measurement efficiency by using sodium sulfate, any salt actually can be used for electrolyte, as electrolyte. I mean, the safe ones, of course. But I mean, to use bias, I mean, usually in the lab measurements, we use bias for like to provide more voltage to investigate the process is working or no. But until it's working and it can be manufactured in the industrial scale, we can use like solar sun as a bias for the providing more electrons to the system to produce hydrogen.
Okay. I think all the answer. Maybe this is the answer, the last question. So that because there's no more question from the audience. I think we have to conclude this, resume this webinar. Thank you very much for Dr. Ibrahim for your very nice presentation today, and I hope that we can continue our collaboration from here from Indonesia to Egypt. We are same. We are from the developing countries, so I think the facility not like in Europe or like in America, but I think since we have a same condition. So what is your what your experience? I think we can share. One of our lecturer here also working in photocatalytic. Yeah. So I think it's close. So we can maybe next we can continue the discussion and so on. Yeah. I would like to give you a thanks for a very big appreciation for your time to share with us. Before we close this webinar, I would like to ask all the audience to open the camera so we can just open the camera and we try to take a photo for the. Okay, for all this audience, just take a photo, open the camera. At least in my record, there is 96 people attend to this webinar. I think this is good because usually we are around 60 until 100. Yeah. And in the name, maybe there is one from Thailand, maybe I don't know, maybe one or two from Egypt. And in the rest is from Indonesia, right? But it's okay. Okay, thank you very much. And I will count. I would like to count. 1, 2, 3. Okay. Next. 1, 2, 3. Next. Okay. 1, 2, 3. Okay. Thank you very much, Brother Ibrahim, for your. Yeah, it's a long time no see because I left England maybe 2009, so it's 12 years ago. But I think
we missed you.
Yeah. Okay. Thank you very much for your.
Thank you very much, brother. Thank you.
Thank you. Today, and thank you. Saya akhiri. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi.
Thank you. Thank you.
Thank you.
Yeah. Yeah, and end the meeting.